Section: Introduction. In this section, we explore the impact of multimodal models like clip and stable diffusion on various tasks. These models have greatly improved tasks such as image recognition and text-to-image generation. We focus on zero-shot generalization, which is the ability of a model to apply its learned knowledge to new concepts it has not seen before. We aim to answer the question: can current multimodal models truly generalize in a zero-shot manner? To investigate this, we compare the performance of models across different tasks and analyze how often new concepts appear in their training data. We compile a list of 4,029 concepts from 27 tasks and evaluate how well the models perform on these concepts. We use 5 large pre-training datasets and test 10 clip models and 24 text-to-image models with various architectures and parameters. Our experiments consistently show that the frequency of a concept in the training data strongly influences the model's performance on test examples related to that concept. We observe a log linear scaling trend, where model performance improves linearly as the concept frequency in the training data grows exponentially. This trend holds even when considering factors like similar samples in both training and test data. We find that the success of models like clip and stable diffusion is mainly due to having test concepts in their extensive training data. This means that their reported performance does not truly demonstrate zero-shot generalization. These models require a significant amount of data on a concept to improve their performance, highlighting their inefficiency in learning from limited samples. We also analyze the distribution of concepts in the training data and find that many concepts are rare, but these rare concepts are not effectively learned during training. Additionally, we observe strong correlations in concept distributions across different training datasets, indicating the need for balancing efforts. To provide a benchmark for generalization performance, we introduce a new test dataset called Let It Wag that controls for concept frequency in the training set. Models trained on both open and closed-source datasets show decreased performance on this dataset, suggesting that our findings may apply to various datasets. We release all our data artifacts to facilitate further research on multimodal models. Our analysis contributes to understanding the challenges in achieving zero-shot generalization with large-scale multimodal models. Section Summary. In this section, we delve into the empirical success of multimodal models like clip and stable diffusion in zero-shot generalization, assessing their performance on new concepts. Our analysis reveals that the model's performance heavily relies on the frequency of concepts in their pre-training datasets, showcasing extreme sample inefficiency and a log linear scaling trend. Despite encountering misalignment and long-tailed concept distributions in pre-training data, our findings suggest that current multimodal models do not exhibit true, zero-shot generalization, emphasizing the need for further exploration in achieving this capability. Section: Concepts in Pre-training Data and Quantifying Frequency. In this section, we outline our methodology for obtaining concept frequencies within pre-training datasets. We first define the concepts we are interested in and then explain how we extract their frequencies from images and text captions in the pre-training datasets. Finally, we discuss how we combine these frequencies to calculate matched image-text concept frequencies. To get an overview of our methods, you can refer to the figure labeled Freq Method Overview. When we talk about concepts, we mean the specific objects or class categories we want to study in the pre-training datasets. For tasks like zero-shot classification, these concepts are the class names, such as the 1,000 classes in ImageNet like tench, goldfish, and stingray. For tasks involving image text retrieval and image generation, concepts are all the nouns found in the test set captions or generation prompts. For example, in the caption, "A man is wearing a hat," we identify man and hat as relevant concepts. We filter out nouns that appear in less than 5 evaluation samples to remove ambiguous or irrelevant concepts. In all our experiments, we compile a list of 4,029 concepts from 17 classification, 2 retrieval, and 8 image generation downstream datasets. To find concept frequencies from text captions, we pre-index all captions from the pre-training datasets by mapping concepts to captions. We use part-of-speech tagging to isolate common and proper nouns, standardize word forms with lemmatization, and create inverted unigram dictionaries. This allows us to determine the frequency of a concept by examining its individual unigrams within these dictionaries. For multi-word concepts, we identify samples containing all parts of the concept by intersecting the lists of sample indices. The frequency of the concept in the text captions is the count of these intersecting sample indices, enabling efficient concept searches. For obtaining concept frequencies from images, we use a pre-trained image tagging model to verify the presence of the 4029 downstream concepts in images. We found that the RAM++ model performs the best for this task. By tagging images based on a predefined list of concepts in a multi-label manner, we generate a list of images labeled with the presence or absence of downstream concepts, allowing us to compute concept frequencies. To calculate matched image text concept frequencies, we identify samples where both the image and its associated caption correspond to the concept. By intersecting the lists from our image and text searches, we determine the count of samples aligning in both modalities, providing a comprehensive view of concept representation across the dataset. This step is crucial due to observed image-text misalignment in the pre-training datasets, where captions may not accurately reflect what is in the image and vice versa. After estimating frequencies for our downstream concepts, we explore the relationship between image-text matched pre-training concept frequencies and zero-shot performance across classification, retrieval, and generation tasks. We analyze two classes of multimodal models, image-text and text-to-image, detailing the datasets, evaluation parameters, and key results. Our findings demonstrate the impact of concept frequency on model performance and reveal a log-linear relationship between concept frequency and zero-shot performance across various tasks and model types. Section Summary. In this section, we outline our methodology for determining concept frequencies within pre-training datasets by defining concepts of interest, extracting their frequencies from images and text captions, and aggregating them to calculate matched image-text concept frequencies. We define concepts as specific objects or class categories in pre-training datasets, extract relevant nouns from text captions, and filter out ambiguous or irrelevant concepts. By pre-indexing text captions and using image tagging models for images, we estimate concept frequencies efficiently and combine them to analyze concept representation across datasets, revealing a log-linear relationship between concept frequency and zero-shot performance in various multimodal tasks. Section. Stress testing the concept frequency performance scaling trend. In this section, we aim to understand how the frequency of concepts affects the performance of models that have not been explicitly trained on those concepts. To do this, we controlled for a factor known to influence model performance: the similarity between the data used for pre-training and the data used for testing. We also wanted to confirm our hypothesis by investigating how concept frequency relates to model performance when the models are trained on data with artificially controlled concept distributions. To control for sample similarity between pre-training and testing data, we conducted experiments using the LAION200M dataset. We first made sure that a specific model trained on this dataset showed a similar relationship between concept frequency and performance as seen in previous studies. Then, we used a method to remove 50 million samples from the pre-training data that were most similar to the test data. Despite this drastic change, we still observed a consistent relationship between concept frequency and model performance. We repeated this analysis with models trained on the modified dataset and found that the relationship between concept frequency and performance persisted, even after removing the most similar samples between the pre-training and test data. This reaffirmed the importance of concept frequency as an indicator of model performance. We also explored how models performed on a synthetic dataset with a different concept distribution. Even in this purely synthetic scenario, we found that concept frequency remained a reliable predictor of model performance. This consistency across real and synthetic data highlights the robustness of concept frequency as a performance indicator. Additionally, we made some interesting observations about the distribution of concept frequencies in pre-training datasets. We found that the distribution is heavily skewed, with most concepts appearing very infrequently. We also discovered a high degree of misalignment between concepts in paired image text data, which had not been quantified before. Furthermore, we identified a strong correlation in concept frequencies across different datasets, suggesting a common long-tailed distribution pattern in datasets sourced from the Internet. Section Summary. In this section, we aim to understand the impact of concept frequency on model performance by controlling for sample similarity between pre-training and downstream datasets. By conducting experiments on both real and synthetic datasets, we found that concept frequency remains a strong predictor of model performance even after removing similar samples. Our analysis revealed a consistent log-linear relationship between concept frequency and zero-shot performance, emphasizing the robustness of concept frequency as an indicator of model performance across different data distributions. Section: Testing the tail. Let it wag. In this section, we identified a consistent long-tailed concept distribution, which shows that certain concepts are rare on the web. This led us to hypothesize that models may not perform well when tested on heavily long-tailed data distributions. To test this, we selected 290 concepts that were the least frequent across all pre-training datasets, such as an A310 aircraft, a worm snake, and a tropical kingbird, to create a classification test set called Let It Wag. The Let It Wag classification dataset consists of 130,000 test samples spread evenly across the 290 categories representing long-tailed concepts. We downloaded test images for these concepts, removed duplicates and outliers, and carefully verified the labels. We then conducted classification and image generation experiments on this dataset. For classification, we evaluated the performance of 40 text image models on the Let It Wag dataset using various prompts. In the image generation task, we used different models to generate images for the rare concepts. Our results showed that all models performed significantly worse on the long-tailed Let It Wag dataset compared to the standard ImageNet dataset, with some models showing improvement for the rare concepts. In the image generation analysis, we found that while descriptive prompts helped improve the quality of generated images, the models still struggled to accurately represent many rare concepts. Some failure cases included misrepresenting activities or generating the wrong concept entirely. Our findings suggest that current multimodal models consistently underperform on long-tailed data, indicating a need for better learning strategies for rare concepts. Our work aligns with previous studies that emphasize the impact of pre-training data on model performance. We show that the frequency of concept occurrences is a crucial factor affecting model performance, especially for rare concepts. Our research complements existing work on dataset composition and data-centric analyses, highlighting the importance of addressing long-tailed concepts in pre-training datasets for future research efforts.